This is Statistics Week 8, Part 7, Population Proportion Problems. Confidence intervals are sometimes stated in terms of proportions or percentages. Here's an example. A poll for a particular candidate running for president might show that the candidate has 40% of the vote within 3 percentage points if the sample is large enough. Often, election polls are calculated with 95% confidence, so the pollsters would be 95% confident that the true proportion of voters who favored the candidate would be between 0.37 and 0.43. That's a confidence interval of 0.40 minus 0.03 and 0.40 plus 0.03. Another example, investors in the stock market are interested in the true proportion of stocks that go up and down each week. Confidence intervals can be calculated for the true proportion of stocks that go up or down each week. Final example would be, businesses that sell personal computers are interested in the proportion of households in the United States that own personal computers. Confidence intervals can be calculated for the true proportion of households in the United States that own personal computers. The procedure to find the confidence interval, the sample size, the error bound, and the confidence level for a proportion is similar to that for a population mean, but the formulas are different. How do you know you're dealing with a proportion problem? First, the underlying distribution is binomial. There's no mention of a mean or average. If x is a binomial random variable, then x is a random variable that is represented by b of np, where n is the number of trials and p is the probability of success. To form a proportion, take the x, the random variable, for the number of successes and divide it by n, the number of trials, or the sample size. So the random variable p prime is that proportion p prime equals x divided by n. When n is large and p is not close to 0 or 1, we can use the normal distribution to approximate the binomial, so that x is represented by n of np and the square root of npq, which, from our discussion of binomial distributions, are the mean and the standard deviation. For the proportion x over n equals p prime, is represented by the normal distribution of np over n, comma, the square root of npq divided by n. Or p prime is represented by n of np over n, and using a little bit of arithmetic, we get the square root of pq over n. Notice also that in np over n, we can simplify that just to p. P prime follows a normal distribution for proportions. The confidence interval has the form P prime minus EBP, P prime plus EBP. EBP is the error bound for the proportion. We will need to change the binomial probabilities P and Q as well to proportional equivalence. P prime will be x over n, and Q prime will be 1 minus P prime. P prime equals the estimated proportion of successes. P prime is a point estimate for P. The error bound for the proportion is given by this formula, which is similar to our others, but again, here we have z of alpha over 2, which is our z-score for a standard normal distribution, but we're going to replace our sigma over n by p prime q prime, square root of p prime q prime over n, which we saw in the last formula, where q prime is 1 minus p prime. Notice that the standard deviation has been replaced. In the error-bound formula, the sample proportions p prime and q prime are estimates for the unknown population proportions p and q. The estimated proportions p prime and q prime are used because p and q are not known. The sample proportions p prime and q prime are calculated from the data. P prime is the estimated proportion of successes, and q prime is the estimated proportion of failures. For the normal distribution of proportions, the z-score formula is as follows. If p prime is a random variable represented by the normal distribution with mean p and standard deviation square root of pq over n, the z-score formula is z equals p prime minus p divided by the square root of pq over n. Here's an example. Suppose that a market research firm is hired to estimate the of adults living in a large city who have cell phones. 500 randomly selected adult residents in this city are surveyed to determine whether they have cell phones. Of the 500 people surveyed, 420 respond yes that they own cell phones. Using a 95% confidence interval, compute a confidence interval estimate for the true proportion of adult residents of the city who have cell phones. Here's our solution. Let x equal the number of people in the sample who have cell phones. X is binomial, so x is represented by the binomial distribution for n 500 and probability 421 divided by 500. To calculate the confidence interval, you must find p prime, q prime, and EBP. So n is 500, x is the number of successes, 421, p prime is n divided by x, which is 421 over 500, or 0.842. This is the point estimate of the population proportion. Q prime will be 1 minus p prime, or 0.158. Since the confidence level is 0.95 and we have a normal distribution, z of alpha over 2, as in our other calculations using inverse norm, will be 1.96. And our error bound for the population will be z of alpha over 2, which is 1.96, times p squared of p prime, 0.842, q prime, 0.158, and our population n, 500. That gives us 0.032, and the 95% confidence interval is p prime minus EBP, p prime plus EBP, or 0.810 and to 0.874. So this is very similar to the other calculations we've done. Here's a try-it exercise for you to work through. So stop the video at this point, work through the exercise, and then start it again when you're ready to view the answer and check your work. Here's our solution. 810. Suppose 250 randomly selected people are surveyed to determine if they own a tablet. Of the 250 surveyed, 98 reported owning a tablet. Using a 95% confidence interval, compute a confidence interval estimate for the true proportion of people who own tablets. Let x equal the number of people in the sample who own a tablet. X is binomial, so x is represented by b of 250 and 98 over 250. To calculate the confidence interval, you must find p prime, q prime, and EBP. So again, for this one, very similar calculation. N is 250. X is the number of successes, 98. P prime is n divided by x, which is 0.392. Q prime will be 0.608. Our confidence level is the same, and our z value, z of 0.025, is 1.96. Our error bound for the population is 1.96 multiplied by 0.392 times 0.608 divided by square 250. That gives us 0.0605, and our 95% confidence interval is 0.332 to 0.453. We can be 95% confident that between 33.2% and 45.3% of people own tablets. One useful technique when we don't have enough information necessarily, or enough in our population, is to use the +4 confidence interval for p. There's a certain amount of error introduced in the process of calculating a confidence interval for a proportion. Because we do not know the true proportion for the population, we're forced to use point estimates to calculate the appropriate standard deviation of the sample distribution. Studies have shown that the resulting estimation of the standard deviation can be flawed. Fortunately, there's a simple adjustment that allows us to produce more accurate confidence intervals. We simply pretend that we have 4 additional observations. 2 of these observations are successes and 2 are failures. The new sample size then is n plus 4, and the new count of successes is x plus 2. Computer studies have demonstrated that the effectiveness of this method, it should be used when the confidence level is at least 90%.